Welcome all to the third video or third lecture on design of beams. In the last video already we have seen section classification. Flange was plastic and web was also plastic. Now here epsilon refers to as the formula given here. It is 250 divided by Fy to the power 1 by 2. 250 divided by Fy to the power 1 by 2. So for Fe 410 grade, Fy is also 250. So 250 by 250, automatically epsilon value will be equal to 1. Now this epsilon value will be equal to 1 for grade Fe 410. For grade Fe 410, epsilon value will be always equal to 1. Now moving ahead with the next step, that is step number 5. Check for shear. Check for shear, it is given in clause number 8.4, page number 59. You can go back and refer to the same formulas you'll find there in the IS 800. So it says Vd is equal to Vn by gamma m naught. So Vd is the design shear capacity. Vd is the design shear capacity. So Vn is nominal shear capacity, that is AV. AV is area of the web into yield strength Fyw divided by root 3. So now Vn is equal to AV into Fyw, that is 250 divided by root 3. AV refers to as per IS 800, will quickly show here. Page number 52. So it is not page number 52. Rather, it has to be. Please make a correction. It is page number 59. It is page number 59. So now the same formula is given here. Vn is equal to, Vd is equal to Vn by gamma m naught. So Vn is equal to Vp. Vn is equal to Vp, and Vp is equal to AV into Fyw divided by root 3. AV is nothing but shear area. AV is nothing but shear area. For I section, for I and channel section, or hot rolled, that is rolled I section, it is calculated as H into Tw. H into Tw. H being overall depth and Tw being the thickness of the web. Now coming back with the calculation, that is actually Vp. This is actually Vp. That is AV is equal to overall depth is 550 into thickness of web is 11.2 into yield strength is 250 divided by root 3. So you'll be getting Vp as 889. So you'll be getting Vp as 889 kilonewton. So now Vp, if it is 889, Vn also will be equal to 889. So now going back, so Vd is equal to Vn by gamma m naught. So therefore Vd is equal to Vn by gamma m naught. So 889 divided by 1.1. So 8 naught, 8 kilonewton. Now this is the design shear capacity of the section. This is the design shear capacity of the section. Now earlier if you look at the bit, actual shear force coming at the section is 252.56 kilonewton. The shear force coming at a section is 252.56 kilonewton. But the design shear capacity is 889. Sorry, 808. So now 808 is very much greater than 252.56 kilonewton. Therefore, it is safe in shear. It is safe in shear. Now coming to the check for bending capacity, or check for bending moment or bending capacity. Now, like discussed earlier, the beam is given as laterally supported. Now, for laterally supported beam, we refer to clause number 8.2.1. So within that, there are sub clauses. We have to check whether the beam is susceptible to buckling or not susceptible to buckling. So for that, you have to check the ratio called D by Tw. So which is already done earlier. D by Tw, which is 45.66. D is nothing but depth of the web divided by thickness of the web. Depth of the web divided by thickness of the web. That calculation we have already done it in the section classification here. D by Tw, which is 45.66. Now that value is less than 67 epsilon. It means web will not susceptible to buckle. It means the web will not susceptible to buckle. So now the reference for this is given in. The reference for this clause is given in 8.2.1. IS 800. You can refer there. If this value is greater than 67, so web will be susceptible to buckling. In that case, we cannot follow the below procedure. So the below procedure should be followed only when web is not susceptible to buckling. Clear? Now for exam point of view, that is why you have to adopt an higher I section. You have to adopt an higher I section. Now going ahead with, as per our calculation, web is not susceptible to buckling. So now going ahead with the next calculation. Next we have to check this clause, whether your V, this is the design shear, sorry, this is the actual shear force, and this is the design shear, 0.6 times of VD. Now the actual shear force or the factored shear force is 252.6, and 0.6 times of VD is 0.6 into the design shear force, which is 484. Yeah, if V is less than 0.6 times of VD, we call it as low shear. If V is less than 0.6 times of VD, we call it as low shear. If V is greater than 0.6 times of VD, we call it as high shear. In our case, it is low shear. If it is a low shear case, we have to refer to this clause. You have to refer to clause number 8.2.1.2. You have to refer to clause number 8.2.1.2. If it is a high shear, we cannot use this clause. If it is high shear, if V is greater than 0.6 times of VD, we cannot use this clause. So that is why, again, like told earlier, you have to use an higher I section. You have to use always an higher I section, so that it will not be susceptible to buckling, and same time it will not be high shear. If you adopt higher I section, higher I section, so your web also will be not susceptible to buckling, and same time it will be a case of low shear. Your V will be less than VD. Yeah, if it is V is less than VD, V is less than VD, 0.6 VD, that becomes a case of low shear. Now, hence, the design bending capacity is calculated as per 8.2.1.2. That is, MD is equal to beta B into ZP into Fy by gamma M naught. So the same formula is given in 8.2.1.2. So now whatever we have discussed, that is what they have given in the statement form here. When the factor design shear force does not exceed 0.6 VD, where VD is the design shear strength, which is already calculated, the design bending strength MD shall be taken as below. That is, MD is equal to beta B into ZP into Fy by gamma M naught. We have the same formula. Yeah. Now one by one, beta B is constant. Beta B is constant, and it will be 1 for plastic and semi-compact section. Sorry, compact section, and beta B is equal to ZE by ZP for semi-compact section. Now ZE stands for elastic section modulus. Now here, as per the section classification, we have already seen that. Yeah, we have already seen that flange is also plastic, web is also plastic. Though entire section will be plastic. So therefore, for plastic section, beta B value becomes 1. For beta B value becomes 1, and this is ZP is equal to 2.712 into 10 to the power 6. This is already property taken earlier from IS 800. This property is already taken from IS 800 into Fy divided by 1.1. So which you will get MD as the design bending capacity as 616.36 kilonewton meter, which is greater than the actual bending capacity calculated in earlier steps. The actual bending moment, sorry, not the capacity. The actual bending moment, how much is that we have calculated? Yeah, the bending moment coming in the section is 450. Maximum bending moment coming in the section at the center is 450 kilonewton meter. But the capacity of section what we have adopted, is capable of resisting a bending moment of 616. Therefore, it is safe in bending. Now coming to the step number 7. Now check for deflection. Now deflection is always checked at the center. Since it is a simply supported beam subjected to UDL and point load, the maximum deflection will be at the center. And one more important thing, our maximum deflection is always checked for the service loads, not the factored loads. It is always checked for the service loads, not the factored loads. And this is the deflection formula for beam. This is the deflection formula for a simply supported beam subjected to UDL. And this is the deflection formula for simply supported beam subjected to point load at the center. Point load at the center, that is 5W L raised to 4 by 384 EI. And this is PL cube by 48 EI. And this has to be taken about XX axis or ZZ axis. your IXX has to be taken from the steel table. So when you refer to the steel table, you'll get IXX for the value, for the section ISMB 550. Now substituting 1 by 1, 5 into 46.25, length of the beam is 6200, so 384. Young's modulus is 2 into 10 to the power 5, and this IXX is taken from the steel table. So when you plus the calculation is the plus this one, the load acting at the center point load is 50 kilonewton, which is converted into Newton, 50 into 10 to the power 3. Even this kilonewton per meter has to be converted to Newton per millimeter, because all other values are in Newton and meter. Now this kilonewton per meter UDL has to be converted to Newton per millimeter. So now P is 50 kilonewton, L is 6200 mm divided by 48, and Young's modulus is 2 into 10 to the power 5, IXX. So now you will get this deflection, actual deflection as 8.76 mm. Now this actual deflection should be less than the permissible deflection. Actual deflection should be less than the permissible deflection. Now the permissible deflection is calculated as L by 300. We'll show the reference L by 300 from table number 6, page number 31. So now L is 6200 divided by 300. So L by 300, that is 20.67. Now actual deflection is 8.76 mm. Actual deflection is 8.6 mm, and the permissible deflection is 20.67. So therefore, actual deflection is less than the permissible deflection. Therefore, the beam is safe in deflection. I'll quickly show where this permissible deflection is taken from. That is page number, table number 6. Table number 6 and page number 31. Table number 6 and page number 31. Now that is a criteria for deflection. So now it says the deflection under serviceability loads. Deflection always have to be checked for serviceable loads. Now it is not an industrial building, so that is why we'll be referring to the other buildings. Now we are checking in vertical deflection. Say we'll refer to the live loads. We are checking for a floor and roof. Clear? So within that there are two subclauses. Say we are considering elements not susceptible to cracking. So it says the permissible deflection or the maximum deflection. So other buildings, vertical deflection, live load, floor load. So elements not susceptible to cracking. So it says span by 300. That is L by 300. Now the same thing was taken here also. Now that is safe in deflection also. So that ends up with the third video. So in the next video, we'll be checking for, we have checked for overall failure. We have checked for bending, we have checked for shear, and we have checked for deflection. Now, these are overall failure check. So therefore, your beam also has to be checked for web buckling and web crippling. So that will be shown in the next video. Thank you.